Welcome to The Kingstonian, a podcast that profiles people who are passionate about what they do for a living, what organization they belong to, or the community they are a part of. Here is your host, Dave Cunningham.
Thank you, Steve. Hello, everyone, and welcome. Climate change. Is it all man-made? How do we measure its impact? What's our timeline? How do we deal with it? We need current information. We need environmental scientists to be as prominent in the media as epidemiologists have been during this pandemic. In this episode, our guest is a highly respected professor in the biology department at Queen's, whose research into the history of climate change is shedding new light on the topic. His name is John Smol. John, thank you very much for agreeing to participate in our podcast today.
Oh, thank you. I'm happy to be here.
You have written some 20 books, and I'm wondering where this interest came from. What started this passion for you?
Well, I think I was always interested in the environment. I think I actually grew up mainly in urban settings, but I grew up sort of in the 60s into the 70s when the environmental movement was sort of gaining steam. And in fact, some would argue even starting in a large way. And from day one, I've always interested in the environment, and I sort of kept that interest. I also always seemed to have some passion for lakes, even though as a young person, I didn't see all that many of them, but it always seemed like a remarkable thing. And so I guess I went to university at McGill, undergraduate, and I guess it never occurred to me that you can actually have a job doing this. You sort of grow up, and the jobs you hear about are, at that point it was like milkman, mailman, garbage man, and then some people were doctors, lawyers, and teachers, and that sort of was your spectrum of careers. It seemed. It's only when you're going to university, so these people can actually make a living working on lakes and stuff. So I guess it's been a passion, and it's been a passion to see how things change over time. I always had an interest in history as well. So the field I chose is working on the environment, especially on lakes, but also on the history of lakes, because I think history is where a lot of answers lay hidden.
How much of your passion involves teaching versus research, or is it the other way around?
Yeah, no, I mean, I divide my career into three. Usually in a university, it depends on how research intensive it is. But in a place like Queen's University, for example, which is a research intensive university, the assumption is that 40% of your time is teaching, 40% of your time is research, and 20% of your time is on service. And that service would include outreach and things like that. Of course, that does assume about a 45-hour week, which I don't do. but teaching is critical. I feel very, very strongly about teaching. I think the whole function, we do research to find answers. So it's knowledge, call it knowledge creation. There's not much use of having knowledge creation if you don't have knowledge communication and knowledge translation. Mm-hmm. And that's where teaching and outreach, or teaching to the broader community, comes. So I feel very strongly about that, and I take it seriously. And so it comes from both ends. One of my proudest things is not just the graduate students who have gone on to excellent careers, but also the undergraduate students who have gotten appreciation for environmental issues and have gone on in careers that it was like an investment in their life that continues on. So it really is, your legacy is somewhat the publications, I suppose, but the real legacy is in the people that you may have affected.
Mm-hmm, mm-hmm. Now, for those of us who never took courses in any kind of the ologies at high school or university, there are lots of scientific terms that people may not know or understand the meaning of. And one of them, you talked about being out on the lakes. And I guess the study of lakes is called limnology?
That's correct. Yeah, people know oceanography, but they don't know limnology. So limnology is sort of the lakeside of oceanography.
Okay. So that's not a bad job to have if you're in a climate that's warm or decently warm to be out on the lake. But I hear you spend a lot of time up in the Arctic as well. So what prompted your interest in getting involved in the lakes and boring down to determine long-term timeframes for some of this stuff?
Yes, well, I didn't even know this field sort of existed, to be honest, when I was an undergraduate student. But I kind of started hearing about it. I thought I was going to be a straight limnologist, go to lakes and just analyze what's there, which is a lot of what we still do. Um, I got a job in between the summer between my undergraduate, which was at McGill, and my master's, which was at Brock University in St. Catharines. I had a job at the McGill Research Station. I was very lucky to be hired as one of the three students who were hired to work as limnologists that summer at their lake station, and which I learned an awful lot, which I certainly acknowledge. But one thing I was seeing these grad students and these professors working at the field station. They were frustrated by they'd get 2 or 3 years of data, and there's a lot of noise in the data. They have an idea, and one year it looked good, and the next year the lake was a little different, and the third year the lake was a little different. And there was a lot of noise. The environment around us is noisy. One year we have a slightly warmer or wetter summer, and then I started realizing there was this field of lakes, and it was a very early field at that time. It really wasn't evolved very much, if you like. But there was this field called paleolimnology, which is the history of lakes, using sediments at the bottom of lakes to reconstruct lake histories. And it's pretty well straightforward type of concept. A lake slowly fills with mud. Lakes in Ontario, for example, are about 12,000 years old, when the last ice age left. When that ice, there was several kilometers of ice sitting on us here in Kingston, and then it got warmer for reasons we understand with the Earth's orbits and everything, and the ice started melting. And one of the legacies of that was the many lakes we have in Kingston and large parts of Canada. That was when the lake formed. That was time zero. Since that time, the lake has slowly been filling with mud or sediment. 24 hours a day, 365 days a year, as mud is accumulating. That's like a time machine going back in time. The very bottom is when the lake started about 12,000 years ago. The very surface is 2021 today. Mm-hmm. And in most lakes in Ontario, there's about 3 meters on average of mud down there. And that's like a history book, 2,000 years old, 3,000 years old, and so forth. And the field was still pretty young when I started. And I'm talking now late 1970s when I first heard the word paleolimnology. It would have been about 77, 78. That seemed like a way that we could integrate data over long time frames. So I was very interested in that, to get rid of some of that year-to-year noise. Mm. So that really became my interest in it. And then especially I was interested in long-term impacts, but also human impacts. And the field evolved very, very rapidly, and now is really used by a lot of people around the world.
Now, did you say you only go down in the lakes in Ontario 2 or 3 meters? Is that as far down as you can go?
Yeah, that's as far as down. For most lakes in Ontario, you can only go back about 12,000 years, because then you hit bedrock. Okay. That's because the glaciers, when they first, when they moved forward, they scraped the land clean. It was like a big bulldozer, several kilometers of ice slowly moving. When it melted, it was this largely denuded landscape, and it filled with water. Now that's in Ontario. There's other areas, and there's some places, there's some exceptions where you can go back further. We worked on one lake on Baffin Island in the Canadian Arctic Islands, and it went back about 250,000 years. There was reasons for that, but those are exceptions in Canada. Mm-hmm. But you can go to places in Africa or Lake Baikal, and you go back millions of years. So it is possible in some of these rift lakes to go back much, much farther. But in Canada, we tend to go back about 10, 12,000 years. But also our work tends to focus on the last 200 years, the period of European impact. Not exclusively, but a lot of what we do is like looking at accelerated human impact relative to natural climate change or natural environmental change. So we're really focusing typically on the last 2 centuries.
I have to ask the question. Have you ever been on Bob's Lake, north of Verona?
I have been on Bob's Lake, yes.
Have you done any sediment checking there?
I think we did, but not in a detailed way, only in a cursory way, but we have been there.
Okay. Yeah. That's just, we summer on Bob's Lake. That's why I had to ask the question.
It's a beautiful lake. Yeah,
it's a big one, lake, too.
Yeah. And complicated. Yeah, complicated lake, yeah.
When you start to look for sediment in these lakes, what are you looking for specifically? If you can put that in layman's terms.
Yeah, so the first thing is you have to get the history book. So the first thing you do is you have to remove the profile of sediment. And we have different ways of doing that. If we're only going for the last 200 years, it's fairly straightforward. The last 200 years, the most lakes in Ontario are occurring in the top half meter, the top 50 centimeters, let's say. And so we have now that's also a very wet sediment. You don't want to mix it up because that's your history book. If you mix it up, you've mixed up 200 years of history. Mm-hmm. So the first step is to remove the history book, and we use different what we call cores, and there's different ways of doing it. But since it's so loose at the surface, I use the analogy of if you have a milkshake, it's about the consistency of surface sediments. That's how loose they are. But you can take a core of your milkshake. You have a straw. You put your straw into the milkshake, and you put your thumb on top of the straw, and you pull it out. You took a core of your milkshake. We sort of do that with a rope, but it's a little more complicated. We send down a core on a rope, which is a tube with a weight on it, and we slowly lower it in the sediment. Then we send what's called a messenger. This lead messenger on the line, and it's like putting your thumb on top of the straw. It closes the top. And so we can remove about 40, 50 centimeters of that very wet sediment. And then we have ways of slowly sectioning about half centimeter at a time. And every time I go deeper and deeper into that core, we're going back in history. So that's the first step, get the core. Now, if you want to go the full 12,000 years, we use a different type. We do the surface core, but then we got the older stuff. We have to push rods, and it's just a different. But it's basically taking a tube of sediment, going back as far as you want.
Now, when you pull out the tube, if you will, the straw, when you pull out the straw and you're looking at the sediment that you've accumulated, what are you looking for in those various layers?
So first we just look at it and we photograph it, but that's not really, there's not that much information there. We might see silt layers where a road came in or something like that. There we're just looking at color, but that's not really much info. What the real information is what's in the mud. And that is where our information comes from. So what's in the mud are three broad groups of what we call indicators or proxy data, things that we're going to try and reconstruct the environment from. Some of it is what we call physical proxies, things like how much sand and silt and clay is in the sediment. That tells you a little bit about erosion, for example. When you have agriculture or a road built, you get erosion, often silt often comes in. So that's one aspect. We can look at the chemistry of the sediments. We can look at, for example, DDT, PCBs, PAHs, these types of these insecticides, they're preserved in the sediment. We can look at the metals, things like lead, cadmium, zinc, mercury, for example, which are different types of contaminants people are worried about. We can look at a whole spectrum of other components. But we do that, but I'm a biologist. I tend to be more interested in what lived in the lake and lived outside the lake. So that's usually in the realm of microfossils. And these are looking for fossils of organisms that lived in the lake. And foremost among those are algae, different types of algae, especially a type of algae called diatoms, which is the most common type of algae. There's thousands of species of algae, but many of them are very well preserved as fossils in the lake. The thing is, different species of algae live in very different environments. Some live only in acid water, some live only in alkaline water, some live in cold water, warm water, some live in salty water, fresh water, high nutrient water, low nutrient water. And a lot of what my lab does is cataloging where all these hundreds and hundreds of species live, and we can get that pretty accurate. And so by knowing what species were there, you can reconstruct the environment. I use an analogy. If I showed you a picture of a polar bear, you'd know quite a lot. Polar bear, you'd know you're in the Arctic, not the Antarctic. First you know you're in a cold area. Then you know you're in the Arctic, not Antarctic, because they're northern hemisphere. You know you're near the ocean because a polar bear eats seal and it needs to be near the sea ice. You'd know quite a lot. It's a specialist. And if I showed you a human being, you wouldn't know that much. Humans live almost all the way to the North Pole, through the tropics. They live everywhere. We're generalists, so we don't give much information. But something like a polar bear, that's the same with all these hundreds of organisms, the fossils we look at. Some are specialists living only in certain environments. Some are broad. And we know that. We can actually quantify that. So we look at fossils of algae. Just give an example. Acid rain I cut my teeth at Queens on acid rain, for example. And acid rain was the big problem in the 1980s when I started my job, early 1990s. The big question then was, have lakes acidified? Well, how do you know if lakes acidified? You have to know what the pH of the lakes was like in the 1800s before acid rain. How are you going to know that? Well, this is a problem. First of all, pH as a function was only invented in 1909. And secondly, certainly no one was measuring pH in the Adirondacks or in Algonquin Park in the early 1800s. They couldn't. But to show that lakes acidified, you had to show they were naturally not acidic, because just like climate change, there were people who denying climate change is happening. At that time, there were certain industries who did not want acid rain to be a problem because we would be pointing the finger at them. And the argument was made repeatedly, yes, the lakes are acid, but they've always been acid. Well, how do you show they haven't always been acid? Well, about the only way you can do that is to show what the pH or the acidity was like in the 1800s. We could use these techniques. We'd go take sediment cores, we find out where the 1800s are, find out what fossils were there, and then reconstruct what the acidity levels of those lakes were.
Now, you mentioned before that there are different conditions in different lakes depending upon where those lakes are. Yeah. One of the things that you did to help address that was put together an organization, and I'm going to try and get this big phrase all out here. It's the acronym is PEARL, and it stands for Paleo-Ecological Environmental Assessment and Research Laboratory. Correct?
Yes. Yeah, so PEARL is our lab at Queen's. I co-directed with Brian Cumming. It's on the 4th floor of the Biosciences building, and it varies the numbers of people, but usually about 35 to 40 people there are actually doing what I'm talking about here. So it might sound like a highly esoteric subject, and it was 30 years ago when I started, but there's clearly some interest in this.
Now, were these people from all over the world or just Queens?
Yeah. We also have visitors from all over the world. These are mainly Queen's graduate students or Queen's people. But we have visitors right now with the pandemic, we don't, but we have visitors coming from South America. I have 3 visitors coming from China as soon as the pandemic is over. So it is also a meeting place of a large number of people. And of course, some of the students and postdocs are from other countries. I have one of the researchers is from Germany, so we are, but it's still largely, it's a Queen's laboratory. And we've worked on all 7 continents. So it's not just in Canada. We're working in large parts of the world, the Arctic, South America, the Andes. There's a lot of problems that need these historical perspectives.
Now, climate change, environmental issues is a very political hot topic, depending upon where you are. You are working with people from all over the world in your research lab. Do you have any sort of common sense that you are all working towards the same goal or finding the same information, or does politics creep in a little bit?
Yeah, well, if you deal with, the quote's been made, environmental science is a contact sport. There is certainly with scientists, 99.99% of science on the climate change, they totally agree on what's happening. But, there are disagreements in subtleties, and that's what science is. Yeah. Science isn't all about people agreeing. Science works because people don't agree. People are always challenging each other. But on the broad, yes, greenhouse gases are the biggest problem facing humanity today. I think 99.9% of scientists are going to agree with that one. But we work on, there are disagreements as there should be in science. The oxygen that drives science forward is criticism, and we're always criticizing each other because that's how no one takes anyone's word for it, So there is sometimes this concept that, it's like sheep following each other. That is definitely not how science functions.
Now, you mentioned something a couple of minutes ago, and I think I want to go back and repeat it because I read something somewhere where you were saying that climate change global warming, not climate change, global warming is the biggest concern right now. It's more important than the pandemic, more important than terrorism, and outline why you think that.
Yeah, I definitely believe that. And I'm not saying the pandemic's not important. I'm not saying terrorism is not important. But if you talk about a global problem that we have to deal with, you hear about things like the economy, and of course they're all important. The environment drives everything. It drives everything. And we are in a race right now. We have waited way too long with climate change. We should have taken action 30 years ago. The data we're in, I've been on this for over 30 years, I think now. And we've stalled and continued to stall. Climate does affect everything, and it's not a cost. How much is it going to cost to deal with this climate change issue? That's the wrong question. The question is, what is the cost of not dealing with this issue, which is tremendous, orders of magnitude more than what anyone is talking about the cost of dealing with it. And it's really for our children and grandchildren. So it affects everything. If you go to the cabinet table in Ottawa or in Toronto, some of the environment is seen as like a cost almost, and it doesn't seem to make much sense to me. The environment, everyone sitting at that cabinet table, the environment is integral, and climate change is integral to their portfolio, from health, but tourism, forestry, agriculture, fisheries. I mean, I'll just keep going, So it's integral. It's not a cost, it's an investment. It's like education, all the cost of education. Well, education is an investment in the future. And it's anyone who does an analysis of it says it's the best investment we can make. Investing in the environment, invest in everything else. So I think it is by far, I mean, it's very serious. Climate change is, I guess I still don't understand why people aren't marching in the streets every day saying we really have to do something about it. Part of it is there's been a well-oiled obstruction campaign that's been going on for 30 years too, of suggesting there's no consensus, which is just nonsense. I mean, and it's been, the science has been in for decades now, and we're just trying to avoid it. It's a sense of we're dealing with denial, really, but we have to. Every time, the longer we wait, we're losing options. We're going to need all the options we can get, so that makes it critical.
One of the things I've noticed, and I think a lot of other people have as well, is that many people are tending to defer to the science when it comes to dealing with the pandemic. They would rather listen to what the scientists are saying rather than the politicians. And I'm wondering if any of that will rub off when it comes to the environment and paying more attention to scientists.
Well, that's a very good point. I'm also president of the Academy of Science of the Royal Society of Canada, and I'm very concerned about science literacy in this country. And I have seen that, and I think you're right. Science has gotten credibility. I am amazed they got the vaccine so quickly. Mm-hmm. I mean, vaccines can take 5, 10. Well, I mean, think of some viruses that don't have vaccines. AIDS has been around for quite some time, and there's still no vaccine. But there was no sure thing that there was going to be a vaccine on this one. I'm amazed how fast the scientists got the vaccines. I mean, it's really, really impressive, and it just shows the power of science. People are going to live because of science, and I think so. I think we should try and keep that momentum going. I think you're right that people there is a growing appreciation that, there's even a song, "Science Nerds Saved Us," but I think we should keep that going. I mean, science is what we see around us. The things we like about our lives came because of science, and but I'm very concerned about how science is treated by certain types of politicians and certain sectors of the community. I mean, there was a time when people who studied an issue for 30 years were called experts. Now it's very easy, at least in some political circles, to call them elites. Mm-hmm. Don't go asking me about how to deal with the GDP, or don't go asking me of how to deal with, even a vaccine, even though I'm a biologist. That's not what I know about. But, I've seen that too. I'm there on television or something talking about climate change. I spent, or some environmental issue. I'm there for 30 years. And suddenly there's this debate with someone else who, as far as I can figure out, is a basement blogger. But it's like, well, obviously there's some controversy here, but it's not an equal playing field. What you hope for, that means nothing in science. What you believe means nothing in science. It's what you can show with data. Mm-hmm. And I says, well, I just don't believe in climate change. Well, it's not a question of belief. I mean, if there's something wrong with what we're saying, could you show us the scientific data? The fact you have this gut feeling means nothing in science. In science, opinions don't mean very much in science. Data matter.
And I think getting the message across is the next big issue that has to be dealt with. And I think there are a couple of common phrases that people have used for years. One of them is thinking outside the box, and the other is communication is everything. And when it comes to getting the message from the science to the general public, who will then tell the politicians, this is what you need to do, and we are prepared to move ahead with the science that is out there. And the question becomes, from your perspective, so you write books, you put articles in journals, you do lectures, you talk on television, radio, and podcasts. And the question then becomes, how do you expand that ability to communicate and get the message across?
Yeah, well, I think things are getting better. I should start by saying that I'm a great proponent, as you know, of outreach, because as we started this podcast, and I think things are improving, but they're improving slowly. I think it's improving, especially with the younger scientists, the upcoming scientists. I think we want to lead by example. And so, this, you can actually do this and it's not detrimental to your career. When I started, I cut my teeth, as I said, on acid rain. A young guy in my 20s, I was doing TV interviews, I was doing radio interviews, and I can tell you at that time, it was not seen as a very positive thing for a university professor to be doing. It was general feeling, he always had this feeling of always trying to blow his own horn, or he's never seen a camera or a microphone he didn't like. And it was just something professors didn't do. It was kind of dirty their hands going out there to the masses. That has changed in universities. I mean, I've seen that. I've seen it in my own career. We have offices in the Queen's University and other universities, communications offices. Their whole function is to get you out there. And we're showing that by example. We even have courses for graduate students on communicating science. We do webinars, we do all those types of things. And in fact, many grant proposals now, there's even special sections on outreach. Okay, here's how you published in journals, that's important. Here's the lectures you gave, that's important. Now, how did you do this knowledge transfer? And that's become a significant component even of grant proposals. So, I think that's all very positive, but it's come slowly, but it is improving. And I think that's really the only way. And the public deserves to know, by and large, all the data we gather in my biosciences building has been paid for by public taxes. I'm amazed we got away with it for so long. I mean, the public has been, paying in their taxes for much of the research that goes on and never really seeing the products of that research. I mean, they saw it indirectly, in some policy, but I think it's high time that we did a much better job of doing that. The public deserves to know is their money being spent? And it would help us as well. The public had an appreciation of what we do and how hard we work and why we're doing it. I think it would even in the long term, increase our possibility of more funding, because people say, well, this is worth doing, rather than some airy ivory tower stuff. So things are changing, but things change slowly.
And like you said, there are courses that the universities are offering to help scientists learn how to communicate. That has to apply to folks like yourself who have been in the business a long time. Now you are an exception, I would say, in terms of being able to communicate, because you do communicate very well, as I've learned over the last 26 minutes. And and I think the whole business of explaining things in terms that people understand, using the analogy of the straw to describe exactly what you do, considering we're on audio and not video. But I think all of that is important in bringing all of that together to get more people paying attention to, like you said, to exactly what you guys are doing.
Yeah. And I think scientists can and should do that. We're not taught, we can get rid of the jargon. Intelligent people who want to know what we're doing will certainly understand what we're doing. And I've heard some scientists say, well, I do something so complicated they won't understand. Well, if that's true, then I don't think the scientist even understands what they're doing. But if you can't explain to an intelligent person of what you're doing and why it's important, you probably don't understand it yourself.
And you shouldn't be getting the grant money.
Yeah, you shouldn't be getting the grant money. Exactly, yeah.
Well, listen, I appreciate your time today, John, and I wish you all the best going forward.
Well, thank you very much.
Professor John Smol from the Biology Department at Queen's University. For more information on the work John's lab does, go to the website queensu.ca/Pearl. This episode was recorded in late May 2021 using Zoom.
The theme music for the podcast is Stasis Oasis, written and performed by Kingston musician Tim Aylesworth. If you have any questions, comments, or suggestions about any of the episodes, please send a note to thekingstonianpodcast@gmail.com. For details on upcoming guests, follow us on Facebook. The Kingstonian Podcast is hosted by Dave Cunningham and produced in Kingston, Ontario, Canada.